All right, hello. I'm going to go ahead and try to do some of the last problems that were on. I'll do a couple of them because I think there was a confusion among some about how to do the series problems. Uh, and you actually need some of these principles to do further um, further work in the course. So let's get to it, and let's break out to this problem here, which I believe was 1C. And you wanted to find the general solution to this. Now remember, when you're using a series method, this is the idea. Let's see if I can get my pen to show up here. There it is. Remember, the idea is that we're looking for a solution, and well, it helps if you got the right thing. And I want to do this. Make sure it's readable. Good. All right, let's get back to it. Remember what we're looking for. We're looking for a hypothetical y equals a naught plus a1 x plus a2 x squared plus a3 x cubed plus the general term is a k x to the k. So we're looking for something like that. Now, and it's first of all, we notice that this is going to have a series solution that's going to be analytic where x squared is by our theorem. That's a coefficient theorem. And so our series is going to be valid on the whole real line centered at 0. Now we need to, of course, get this. We can differentiate this term by term on its interval of convergence. Now we're not going to actually end up using y prime in this one. So it's, I just screwed that up, didn't I? I got too caught up with babbling and not enough paying attention. So you differentiate a naught, you get a 0. And let's go back to this. And plus 2a2x plus 3a3 x squared. This is just calculus differentiation. We're not going to really use y. We're going to use y double prime because it's in the equation. So it's 2a2x. Did it again. Let's go back here and get rid of that. Plus 3 times 2 a3x. And it doesn't hurt to figure out what the general term here is. Because remember, you're differentiating this. So this is going to be k, let's say plus 2, k plus 1. I'm writing this as k plus 2 power. And this is going to be x to the kth power, like so. And all that is from differentiating a polynomial twice. Now I'm going to multiply this x squared minus x squared times y. Now notice, since everything here is going to be that, the very first term is going to be a naught minus a naught x squared minus a1 x cubed minus a2 x to the 5th. And our general term is going to be a minus, put some dots here. And the a kth term is going to be a k minus 2 x. And remember, that's going to be the kth power. Because remember, this bumps up everything by 2, right? So let's say ak times x squared is ak xk plus 2. I want to line. Now, remember, the whole idea is that we'd like to line these up. So you put this into the differential equation like so. And what do we get? Well, we do have a 2a2 plus 3 times 2a3 x. And the first time we get is something with this. So we're going to get the x squared term is going to be 4 times 3 times a to the 4th x squared minus a naught. The next term, see if we can get the pattern there, will be 5 times 4, a to the 5th, minus a to the 1st, x cubed. And if we just keep going, and I'm going to go ahead and shift the indices here, on the x to the k term, we're going to have k plus 2, k plus 1, a to the k plus 2, minus a to the k minus 2, xk. And remember, the whole thing is that all of these have to add to 0. They all add to 0. So because remember, this whole thing has to be 0 for all x. That means every coefficient has to be 0. So 2a2 is 0. 6a3 is 0. So that means these two are zeros. And now your relation here is you have 12a4 is equal to a naught, which means a4 is 1/12 a naught. In fact, we can get to the general relation here. Now I'm going to use this. This says k plus 2 up k plus 1, a k plus 2 is equal to a k minus 2. Now, how I'm going to do this is you got a k plus 2 and a k minus 2. What I'm going to do is I'm going to bump this power up to make that an ak and make that k plus 4. So this is now really k plus 4, k plus 3, a k plus 4 is equal to ak. So that's our general recursion relation right here. So let's go ahead and make this a little smaller, make this a little bigger at the same time. Okay, good. So make this bigger. Now, let's go down here. So what we know, a naught is not resolved. A1 is not resolved. But A2 and A3 are 0. So what that tells us in our general solution that we had right here, our general solution, we don't know what A naught is. That might be an arbitrary constant. A1 might be an arbitrary constant. That's a 0 and that's a 0. So let's just go ahead and just let's do a little bit of solving. A4 is, we said, is 1/12 A naught. And then A8 is, by using this relation right here, it's going to be A4 divided by, that's going to be an 8 and a 7. But that's a, substituting for A4, that's A naught, 8, 7, 4, 3. Let's do one more. If you go up by 4 more, that's A12. That's going to be A8 over 12 times 11, which is equal to, well, A naught, substituting for A8, 12, 11 times 8 times 7 times 4 times 3. So we can get one of our solutions right away. So one solution, let's call that y1, will be A naught. That's not resolved. That's a first coefficient. Then this is going to be 1/12 A naughts, and that's a fourth coefficient, A sub 4, so that corresponds to x to the 4. This A to the 8 corresponds to x to the 8. And then let's go to the other one. That's 1/12. Remember, this is 8. 8 times 7 times 4 times 3, x to the 12th. So that's one of our linearly independent solutions. Our next one, let's call it y2. Notice we have an A1 that's not resolved. That's a coefficient for x. Then the next one is going to be A to the 5th. Well, we can use this relation here. A5 is equal to, that's with k equals 1. So it's going to be A1 divided by 5 times 4. But since it's A to the 5th, we get that. Let's go, 5 plus 4 is 9. So remember, our when we do that, well, remember this thing here for this being 9, that'll be a 9 and an 8. And then that's going to be A5 here, but then we already did that one. So it's 5, 4, x9. And I think we got the pattern here. Let's go up by 4 one more time. That's going to be x9 plus 4 is 13. 13, 12, 9, 8, 5, 4. And those are your two linearly independent solutions. Okay? So you see, it's a matter of just taking these things and gathering up your terms, and then writing a few of them out like this. I think that's probably the easiest way to do that one. Now, let's go ahead and do the next one. This is number 4. Now here, one method, and I'm not going to do it this way, but note, whoops, I don't want it that. I screwed that up. I want to get to this and make sure it's, there we go. Now let's just use a different color here. Now, one of the things to notice is that e to the x is analytic, and you can use this and multiply it out. And so you could go ahead and do that, but that's a real, no one wants to do that. I'm going to use the alternative way. And what I'm going to do is I'm going to notice that my y, written as a Taylor series, is y0 plus y prime 0 times x plus y double prime 0, x squared over 2 factorial plus y triple prime 0, 3 factorial x cubed. I'll do one more, but then this can keep going. This is just Taylor's theorem, or the Maclaurin series, however you want to write it. And now I'm going to use the information we have here. So our y double prime is actually equal to minus e to the x y. So y double prime of 0 is minus e to the 0 times y0. But y0 is given to be 1, and e to the 0 is 1. So that's -1. So let's record our work. like so. Now let's differentiate this again. So it's minus e to the x, y, minus e to the x, y prime. And let's just gather the terms here. This is going to be minus e to the x, y plus y prime. So y triple prime of 0, you plug in 0 for x, it's a minus 1. And here we go. Y of 0 is 1. Y prime of 0 is 0. So y triple prime of 0 is negative 1. Now that we have that, let's differentiate again. So we have a minus e to the x, y plus y prime, minus e to the x. Now we got to differentiate this. Now what I'm going to do is I'm going to combine these just because it makes it a little easier. So you get a y, there's two y primes, and there's a y double prime. Whoops, let's get rid of that. Straight mark. Now, y fourth part of 0, it's negative 1. And then we get a 1. That's what y of 0 is. Y double prime is a negative 1, as we see here. So we get the fourth derivative of 0 is 0. And we can keep this up. The fifth derivative. Well, I'm going to differentiate this. So it's minus e to the x. Minus e to the x. Y prime plus 2y double prime plus y triple prime. And let's lower this down a little bit. So, getting back to here, y the fifth. Now I'm doing this consolidation just because, now let's see, we have plus 3y prime. We have 2y double primes. So with 2 plus 1 is 3. And then we have a triple prime. So I've just combined the y primes, the y double primes, and the triple primes. So yeah, you're right. So plugging in 0, minus 1. Then we have a 1. That's a 0. We have a minus 3 here. And another minus 1. So that's a minus 1 times a minus 3 is 3. So we record that. And let's just go ahead and do the first few terms here. So our hypothetical y, we just plug into Taylor's theorem. And let's remember what we have up here. Let's see here. I'm trying to get this to show up. All right, yeah, so we have negative, okay, so we have because of the original problem, we have a 1, 0, that's a 1, that's a 0, that's given to us, and we calculated these other things. So, remember, we're plugging into Taylor's theorem. So it's going to be y0, which is 1. There's x, y prime of 0 is a 0, so it's plus 0x. Third one is negative 1 x squared over 2 minus x cubed over 3 factorial. The fourth derivative we said is 0. The fifth derivative is 3x to the fifth over 5 factorial. So what we end up with is a 1 minus 1/2 x squared minus x cubed over 6 plus 3 x to the 5th over 5 factorial. That works out to 120. And you can keep going. But you see, that's how you end up. This is the kind of thing you go. Now remember, this is a series, so the terms will go on and on and on. So anyway, I sure hope that helps. As you can see, some of you who didn't get it totally were actually kind of close. And I think this will help you out. Thanks for watching.